You can put a complex number in an Argand diagram. The Argand diagram is like a 2D coordinate system. The horizontal axis is the real axis and marked as RE. All real numbers are on the real axis, like -3, -2, -1, 1, 2, 3. The vertical axis is the imaginary axis and marked as IM. All imaginary numbers are on the imaginary axis, like -3i, -2i, -i, 2i, 3i. The two axes cross at the origin, which represents 0. For example, for the complex number 3 plus 2i, you find 3 on the real axis and 2i on the imaginary axis. The point at the crossing represents 3 plus 2i. The modulus of z is the distance from the point to the origin. Z's modulus is √3 squared plus 2 squared, which is √13. Z's argument is written as argz, or theta. It is the angle of the line with the positive real axis. The argument value is in radian. It is either greater than -pi and less than or equal to pi, or greater than or equal to 0 and less than 2pi. You may use either interval, unless the question specifies otherwise. Tangent of argz is 2/3. It is in the first quadrant, so argz is inverse tangent 2/3, which is 0.59 radian. Remember, argument should be in radian. For a random complex number z, which is equal to a plus bi, its modulus is the root of a squared plus b squared. The tangent of its argument is b/a. When you try to find argz, it's better to sketch the Argand diagram to decide its quadrant and the exact angle value. Find the modulus and argument of u equals 1 minus 2i. Let's plot it in the Argand diagram. It's in the fourth quadrant. U's modulus is √1 squared plus 2 squared, which is √5. Tangent theta is -2. It's in the fourth quadrant. So its value is inverse tangent -2, which is -1.11. Find the modulus and argument of v equals -1 plus 2i. Let's plot it in the Argand diagram. It's in the second quadrant. V's modulus is √1 squared plus 2 squared, which is √5. Tangent theta is also -2, but it's in the second quadrant. So arg v is pi plus inverse tangent -2, which is 2.03. Z and Z's conjugates real parts are the same, and their imaginary parts are opposite of each other. Therefore, Z and Z's conjugate are reflections of each other in the real axis. When we add or subtract two complex numbers, we add or subtract their real parts and imaginary parts separately. When we add or subtract two vectors, we add or subtract their x and y components separately. For example, two complex numbers u and v. U is 1 plus 2i. V is 3 plus 4i. U plus v is 4 plus 6i. Similarly, two vectors u and v. U is 1i plus 2j. V is 3i plus 4j. U plus v is 4i plus 6j. We know we can use parallelogram rule when adding two vectors. Since complex numbers and vectors follow the same rule when adding and subtracting, the two complex numbers will have the same feature on the Argand diagram, or they will follow the parallelogram rule when adding. Two complex numbers u and v. U is -1 plus 2i. V is -3 plus 4i. V minus u is -2 plus 2i. Similarly, two vectors u and v. U is minus 1i plus 2j. V is minus 3i plus 4j. V minus u is minus 2i plus 2j. We know vector uv is v minus u. So on the Argand diagram, complex number v minus u is a vector from u to v. In general, z minus u is a vector starting from u. For example, z minus 1 plus 2i represents vectors starting from point 1, 2i, where z is a random complex number. Remember this important fact. We will use it later in loci. In this class, we learned Argand diagram has a real axis and an imaginary axis. A complex number z equals a plus bi can be put in the Argand diagram. Z's modulus is root a squared plus b squared. Argument arg z is the angle in radian with the positive real axis. Tangent arg z is b over a. The argument is either between minus pi and pi, or 0 and 2 pi. Sketch the Argand diagram to help find the argument. Z and z's conjugate are reflections of each other in the real axis. Complex numbers and vectors are similar geometrically. Z minus u is a vector starting from u, where z is a random complex number.